Okay, to begin to understand Newton's theory of gravity, we need to start with a trip through astronomical history. So if we go back to, uh, you know, BC times, where the Greeks were, um, the primary train of Western thought, the Greeks preferred the geocentric model of the solar system, where you had the Earth at the center, and then everything revolving around the Earth in nice, circular, pure orbits. This is what's often known as the Ptolemaic system. Ptolemy was Egyptian, 2nd century or so. Excuse me. He also was a proponent of this Earth-centered system of the solar system, where everything, including the sun and the planets, all revolved around the Earth in nice, pure, circular orbits. One of the weird things about this is, in order to explain the paths the planets take, they had to explain this retrograde motion where the planets actually appear to stop and go in a loop and then continue on their orbit, which was kind of strange because it didn't really fit anything else observed, but it fit this Earth-centered system. So over the course of the Middle Ages, things began to shift that led us eventually to Newton and his theory of universal gravitation. Began with Copernicus, the Polish astronomer. I think it was, let's see, 15, gotta get my dates right, 1543, where he first proposed the heliocentric view. Now, it was known that this was a view that was out there even in the ancient Greek times, but it wasn't the dominant view that was picked up by the church. Right? This model was agreed upon by the church because God created the earth was the center of the universe. That made sense to them. But this heliocentric model was introduced by Copernicus in 1543, and then over the course of the next century, a series of observations, a series of determinations were made that supported this view. From Copernicus, we have Tycho Brahe, whose apprentice was Johannes Kepler. We'll learn about Kepler's laws, and that's late 1700s, or I'm sorry, late 1500s, early 1600s. And that led to the idea of elliptical orbits versus circular orbits. This Kepler went right into the age of Galileo and the telescope, where we began to look at the heavens now and get some details. Jupiter had moons, just like the Earth has a moon. Well, if the Earth was the center of everything, why don't Jupiter's moons revolve around the Earth? The phases of Venus. There were some new observations made with the telescope that more supported the Copernican view. And then finally Newton, who built upon these ideas to develop his universal theory of gravity. So from an apple to the moon. So the common legend is that Newton saw an apple fall, thought, well, if the apple falls from gravity, the moon falls from gravity. And that's kind of true. It says in his paper that he contemplated on the falling of an apple towards the Earth and said, basically, well, if the apple falls to the Earth due to the Earth's gravity, what if the moon is actually falling to the Earth as well? Because they did know that the moon rotated about the Earth in a circular or almost circular orbit, near circular orbit. So he hypothesized that the same force pulling the apple to the Earth could be the same force pulling the moon towards the Earth, but that actually the moon was in free fall around the Earth. Now, how could that be? How could you be in free fall but be falling around the Earth? Well, since the moon was known to be falling in a circular path around the Earth, if there's a force pulling inward on the moon, but it's got some tangential velocity, you could see that at every position, this force could be a centripetal force, the force of gravity, and the orbit as it changes around the Earth changes direction, right, with this centripetal force. So this was his hypothesis, and the way he went about proving it or testing it was kind of neat. He basically said that if this were true, G, which was known to be about 9.8 meters per second squared, is due to the same force as the moon. This G, this acceleration in terms of the moon's orbit, would be a centripetal acceleration, which would follow v squared over the radius. And this would be the velocity of the moon over the radius of the moon. Now, there were some known quantities at the time of Newton. What was known from astronomical observation was the radius of the moon was pretty accurately known to be 3.84 times 10 to the 8th meters, measured using parallax and using looking at the moon from different points on the Earth and calculating the angles. What was also known, the radius of the Earth, as about 6.37 times 10 to the 6th meters. And what was well known was the speed of the moon, because the period of the moon, or the length of a month, right, the time it takes for the moon to travel around the Earth, 27.3 days, was well known. So if we look at his hypothesis, if the moon's force of gravity was causing its circular path, its centripetal force causing the centripetal acceleration, there must be some relationship between the acceleration due to the force of gravity on the moon from the Earth and due to the apple on the Earth. So here's what he did. He basically said, well, if I take 2 pi r over the period and square it, right, that's my velocity of, or the linear speed of the moon as it travels in a path around the Earth. If I deduce this, I get 4 pi squared r squared over t squared over r, which cancels out one of the r's. And if you calculate that out, you get about 0.00272 meters per second squared. Okay, not 9.8 like is measured on the surface of the Earth. So, well, what begs this difference? Well, what he did was he compared the two. He took that centripetal acceleration of the moon and looked at how it compared to G as measured on Earth. And what he found was the ratio was about 1/3600th as big. So the centripetal acceleration of the moon is less than the acceleration due to gravity on Earth by about 1/3600th. Well, what he did that was fascinating from this is he then compared the radius of the moon to the radius of the Earth. Okay? And when you do that, now this is the radius of the moon's orbit, so to the center of the moon, from the center of the Earth. What you see is it's about 60.2 times farther the surface of the Earth. So the radius of the Earth takes you to the surface of the Earth. The radius of the moon takes you to the center of the moon. So 60 times greater to the radius to the center of the moon from the center of the Earth than from the surface of the Earth. Well, what's comparison between these two numbers? 3600 is approximately 60.2 squared. So what he saw from this is that the strength of this acceleration isn't proportional to the radius, but that the strength of that acceleration is proportional to 1 over the radius squared. So you kind of see a mathematical connection that actually the force of gravity on the apple and on the moon can be from the same force, from this attractive force between the moon and the Earth. And since it's an attractive force, there has to be a counterforce, right? If there's always a second force, an action-reaction pair. So if the Earth pulls on the apple, apple pulls on the Earth. The Earth pulls on the moon, moon pulls back on the Earth. And he used this as a way of developing his formula. So when you look at this universal gravitational formula, G m1 m2 over the distance squared, okay, this comes from Newton's observations that the centripetal acceleration of the moon as it falls around the Earth is proportional to its distance, just like the force or the acceleration of an apple on Earth is proportional to its distance from the center of the Earth. And that's where he got his basis for Fg equals Gmm over r squared. It wasn't proven till later when Cavendish was able, with very sensitive torsion balance, to see that large mass attracts a small mass and it'll get it to displace a certain distance due to this universal force of gravitation between any two masses. And if you can see, if you're finding the acceleration of the moon, which would just be m times the acceleration of the moon, the mass of the moon, right? This acceleration is really based upon the mass of the Earth, g, the gravitational constant, and then the distance from the center of the moon to the center of the Earth, this radius. And that's from an apple to the moon. Hopefully that gives you a little better understanding of where the universal law comes from.